Have you ever stood outside on a clear night, gazing up at the stars, and noticed something strange? No matter where you are, whether you're in a bustling city or a remote desert, whether you're in the northern hemisphere or the southern, the universe looks almost identical. The same constellations, the same distant galaxies, the same vast cosmic tapestry. It's as if the universe has a blueprint, a grand design that repeats itself endlessly across the unimaginable expanse of space. But why? Why is the universe the same everywhere? This isn't just a casual observation. It's one of the deepest mysteries in all of science, a puzzle that has baffled astronomers and physicists for decades. And today, we're going to unravel it together. Think about it for a moment. The universe is unimaginably vast, stretching over 93 billion light-years across, filled with uncountable galaxies, stars, and planets. Yet, despite this mind-boggling scale, the laws of physics, the distribution of matter, even the faint glow of radiation left over from the birth of the cosmos, they're all eerily uniform. It's like walking into a room where every corner, every wall, every detail is perfectly identical, no matter how far you go. How could something so enormous be so consistent? The answer lies in the very origins of the universe itself, in the explosive moment of creation we call the Big Bang, and in the subtle clues hidden in the oldest light in existence. This isn't just a story about distant stars or abstract physics, it's a story about us, because the uniformity of the universe isn't just a cosmic coincidence, it's the reason we exist at all. If the universe weren't so perfectly balanced, if its structure weren't so finely tuned, life as we know it would never have had a chance to emerge. So as we dive into the science behind this universal sameness, we're not just exploring the secrets of the cosmos, we're uncovering the very conditions that made our existence possible. From the echoes of the Big Bang to the mysterious force of inflation that shaped the early universe, we'll piece together the evidence that explains why the night sky looks the same no matter where you stand. And by the end, you'll never look up at the stars the same way again. The cosmological principle isn't just some abstract idea scientists dreamed up. It's the foundation of everything we know about the universe. Picture the cosmos as an endless ocean where no matter which direction you sail, the water has the same temperature, the same saltiness, the same currents. That's how our universe works on the grandest scales, but here's what's truly mind-blowing. This uniformity tells us something profound about the origins of everything. Rewind time nearly 14 billion years to a fraction of a second after the Big Bang. The entire universe was smaller than a single atom, hotter than the core of any star, and packed with unimaginable energy. In those first fleeting moments, something extraordinary happened, a period called cosmic inflation, where space itself expanded faster than the speed of light. This wasn't just any expansion. It was like blowing up a balloon to the size of a galaxy in less time than it takes to blink. And that explosive stretching smoothed out all the wrinkles, ironing out any irregularities until matter and energy were spread almost perfectly evenly across the newborn cosmos. But how do we know this actually happened? The evidence is written in the oldest light in existence, the cosmic microwave background, a faint glow that fills every corner of space. When scientists mapped this ancient radiation, they found it was nearly identical in all directions, with only tiny variations, like the faintest brushstrokes on a vast canvas. Those minuscule fluctuations, smaller than 1 part in 100,000, were the seeds that eventually grew into galaxies and clusters of galaxies. Without that initial near-perfect uniformity, the universe as we know it couldn't exist. here's the beautiful part. This isn't just about distant galaxies or abstract physics. That primordial smoothness made life possible. If the early universe had been too lumpy, matter would have clumped together too quickly, collapsing into black holes before stars could form. Too smooth, and matter might never have gathered enough to create galaxies at all. We exist because the universe struck that delicate balance, uniform enough to be predictable, varied enough to create structure. It's a reminder that the cosmos isn't just out there. Its deepest laws are woven into everything, including us. The Big Bang wasn't just the beginning of time and space. It was the ultimate cosmic reset button, wiping the slate clean and setting the stage for the remarkably uniform universe we see today. Picture the newborn cosmos as a pot of boiling water, churning with unimaginable energy. Every particle, every ripple of radiation was packed so tightly together that they reached thermal equilibrium, like a perfectly mixed batter where every spoonful has exactly the same consistency. This scorching primordial soup was so intensely hot, reaching temperatures of over 10 trillion degrees, that any variations in density or temperature were instantly smoothed out, erased by the sheer violence of the early universe's expansion. But here's where it gets even more fascinating. That initial smoothness alone couldn't explain why the universe remains so uniform across distances that light hasn't had enough time to travel between since the Big Bang. It's like having two identical paintings on opposite sides of the world, painted by artists who never met or communicated. How could they possibly match? The solution lies in a fleeting but pivotal moment called inflation, when the universe expanded exponentially faster than the speed of light in the first fraction of a second after creation. During inflation, space itself stretched so rapidly that microscopic quantum fluctuations, tiny wrinkles in the fabric of reality, were stretched to cosmic proportions, creating the faintest imprints of unevenness. These minuscule variations became the cosmic blueprints for all structure in the universe, from galaxy clusters to the voids between them. Yet, even with these slight differences, the overall uniformity remained intact, preserved by inflation's smoothing effect. It's as if the universe took a deep breath and expanded so quickly that any potential lumps or irregularities were stretched into near-perfect smoothness, like pulling taffy until it becomes thin and even. This delicate balance between uniformity and variation is why we see both the breathtaking consistency of the cosmic microwave background and the intricate web of galaxies filling the cosmos. Without that initial near-perfect smoothness from the Big Bang, followed by inflation's lightning-fast expansion, the universe might have collapsed back on itself or torn apart before stars could ever form. Instead, we inhabit a Goldilocks cosmos, not too chaotic, not too sterile, but just right for the story of matter, life, and us to unfold. Inflation theory might sound like something out of science fiction, but it's the most compelling explanation we have for why the universe looks so strikingly similar in every direction. Imagine blowing up a balloon with tiny dots drawn all over it as the balloon expands. Those dots move farther apart, but the pattern remains evenly spaced. That's essentially what happened to the universe in its first fleeting moments. In less time than it takes for light to cross a single atom, space itself stretched exponentially, smoothing out any clumps or variations like a cosmic iron pressing out wrinkles in the fabric of reality. This wasn't just a gentle expansion, it was a runaway explosion of space, doubling in size over and over again, faster than the speed of light. And here's why that matters. Without this ultra-rapid stretching, the universe would be a patchwork of wildly different densities, some regions crammed with matter, others nearly empty. Instead, inflation left us with a cosmos so finely balanced that the temperature of the cosmic microwave background, the afterglow of the Big Bang, varies by less than 100,000th of a degree across the entire sky. But how do we know inflation actually happened? The smoking gun lies in those tiny temperature fluctuations in the ancient light. Think of them as cosmic fingerprints, the faint echoes of quantum jitters from the universe's first moments. Inflation stretched these microscopic ripples to astronomical scales, leaving behind a telltale pattern that matches predictions with astonishing precision. Even more compelling, inflation explains why the universe appears flat, not like a sheet of paper, but in the sense that parallel lines stay parallel no matter how far they travel, a geometric consistency we'd only expect if space had been stretched smooth in its infancy. Critics once argued that inflation was too elegant, too convenient, a theory tailored to fit the evidence after the fact. But over decades, the data has piled up, from the detailed maps of the cosmic microwave background to the large-scale distribution of galaxies, all aligning with inflation's predictions. It's as if the universe left us a trail of breadcrumbs, each one leading back to that unimaginably brief moment when everything we know was forged in a fireball of exponential expansion. And without it, the night sky wouldn't be a familiar tapestry of stars. It would be a chaotic jumble, unrecognizable from one patch of space to another. That faint glow you hear about the cosmic microwave background isn't just some abstract scientific concept. It's the oldest photograph ever taken, a snapshot of the universe when it was just 380,000 years old. Picture this: after the Big Bang, the cosmos was a searing plasma of particles and energy, so dense that light couldn't travel more than a tiny distance before bouncing off another particle. But as the universe expanded and cooled, electrons and protons finally combined to form neutral atoms, and suddenly, light could move freely for the first time. That first burst of liberated light is what we now detect as the CMB, stretched over billions of years from visible wavelengths into the microwave part of the spectrum, a relic of creation itself. What's astonishing isn't just that this ancient light still exists, but how eerily uniform it is. No matter where astronomers point their telescopes, the temperature of the CMB hovers around 2.7 degrees above absolute zero, with variations so small they're measured in millionths of a degree. It's like baking a cake where every single crumb, no matter how far apart, has nearly identical texture and flavor. But hidden within that near-perfect smoothness are the faintest ripples, tiny fluctuations in density that hold the key to everything we see today. These imperfections, smaller than 1 part in 100,000, were the gravitational seeds that eventually grew into galaxies, stars, and planets. Without them, the universe would be a featureless void, devoid of structure or life. So how do scientists decode these subtle cosmic whispers? Cutting-edge tools like the Planck satellite and the Atacama Cosmology telescope map the CMB with jaw-dropping precision, measuring temperature differences smaller than a snowflake's weight. These instruments aren't just cameras, they're time machines, peering back to an era when the universe was 1,000 times hotter and 1 billion times denser than it is today. By analyzing the patterns in this primordial light, researchers can test theories like inflation, measure the universe's shape, and even weigh invisible dark matter. The CMB isn't just a relic, it's a Rosetta Stone for cosmology, translating the universe's infancy into a language we can understand. And here's the humbling part. When you look at a static-filled TV screen, about 1% of that noise is actually the CMB, the afterglow of creation, buzzing quietly in the background of everyday life. It's a reminder that the universe's grandest secrets aren't locked away in some distant corner of space. They're all around us, woven into the fabric of reality, waiting to be uncovered. The Planck and WMAP telescopes didn't just observe the cosmic microwave background, they transformed it into a celestial treasure map, revealing the universe's hidden architecture with breathtaking precision. Imagine taking a photograph where every pixel represents a patch of sky 3 times wider than the full moon, yet captures temperature variations smaller than 1/1000th of a degree. That's what these orbiting observatories achieved, compiling years of data into all sky maps that show the afterglow of creation in staggering detail. What they found was both reassuring and puzzling. Across billions of light years, the cosmos displays a near-perfect uniformity, with temperature fluctuations following patterns that match inflation theory's predictions down to the decimal point. Yet even in this sea of sameness, strange ripples emerge. One of the most baffling is the so-called axis of evil, an unexpected alignment of temperature fluctuations that seems to defy the cosmological principle's assumption of universal isotropy. It's as if someone drew faint arrows across the sky, all pointing in the same direction. Then there's the mysterious cold spot, a region billions of light years wide where the CMB is significantly chillier than surrounding areas, like a cosmic frostbite mark that current models struggle to explain. These anomalies aren't just statistical flukes, they persist even after accounting for instrument errors and galactic interference, nudging scientists to consider whether our understanding of cosmic uniformity might need revision. What makes these findings so revolutionary is how they bridge the very large and the very small. The patterns etched into the CMB originate from quantum fluctuations smaller than a proton during inflation, stretched to astronomical scales by the universe's explosive growth. When Planck's measurements matched theoretical predictions to within 1% accuracy, it wasn't just a victory for inflation theory, it was a demonstration that physics operating at scales 1 trillion times smaller than an atom could shape the entire observable cosmos. This incredible connection between micro and macro shows why the CMB isn't just ancient light. It's a forensic record of the universe's first trillionth of a second, waiting to be decoded. The real magic lies in how these observations converge. Satellite data aligns with ground-based telescopes like the Atacama Cosmology Telescope, while independent measurements of galaxy distributions and dark matter maps all tell the same story, a universe that's overwhelmingly uniform, but with just enough variation to spawn the rich tapestry of structures we see today. It's a delicate dance between predictability and surprise, where each confirmed prediction strengthens our models while every anomaly hints at deeper layers of cosmic truth waiting to be uncovered. Those delicate ripples in the cosmic microwave background, those tiny temperature variations smaller than 1 part in 100,000, held the secret to everything we see today. Over billions of years, gravity took those faint whispers of unevenness and sculpted them into the breathtaking cosmic web we now observe. Vast filaments of galaxies stretching across the void like threads of light, intersecting at massive clusters containing thousands of galaxies, all separated by enormous, almost empty voids. It's a structure so immense that single filaments can span hundreds of millions of light years, yet it all sprang from those nearly imperceptible density variations in the infant universe. Here's what's truly remarkable. While these structures are staggeringly large, they're just wrinkles on an otherwise smooth cosmic fabric. Zoom out far enough, and the universe still looks uniform, like standing back from a tapestry until the individual threads blur into a single, consistent pattern. This delicate balance between structure and homogeneity comes down to 2 invisible players, dark matter and dark energy. Dark matter acts as the universe's scaffolding, an invisible framework that guided the growth of cosmic structure. Unlike ordinary matter, dark matter doesn't interact with light or electromagnetic forces, it only feels gravity's pull. That means in the early universe, while normal matter was buffeted by radiation pressure, dark matter could quietly clump together, forming gravitational wells that eventually drew in gas and dust to create galaxies. Without dark matter's steadying influence, those initial density fluctuations might never have grown into the intricate cosmic web we see today. Yet, just as dark matter helps build structure, dark energy works in opposition, stretching space itself and pushing galaxies apart. Discovered in the late 1990s through observations of distant supernova, dark energy explains why the universe's expansion isn't slowing down as expected but accelerating. On small scales, gravity still dominates, allowing galaxies and clusters to hold together. But on the largest scales, dark energy's repulsive force ensures the cosmos remains homogeneous, preventing matter from clumping too densely across the grandest distances. This cosmic tug-of-war creates the universe we inhabit, one where galaxies cluster along filaments like pearls on a necklace, yet when you step back, the overall distribution remains smooth. It's a delicate equilibrium, too much dark matter, and the universe might have collapsed back on itself long ago. Too much dark energy, and galaxies would be torn apart before stars could ever form. Instead, we live in a Goldilocks cosmos where both forces coexist, shaping a universe that's structured enough to create galaxies, life, and us, yet uniform enough to follow predictable, universal laws no matter where you look. Dark matter is the universe's silent architect, shaping the cosmos in ways we're only beginning to understand. Think of it as an invisible framework, a hidden skeleton that holds galaxies together and guides their movements across the vastness of space. Unlike the ordinary matter that makes up stars, planets, and everything we can see, dark matter doesn't emit, absorb, or reflect light. It's completely transparent. You could pass right through a cloud of dark matter and never know it was there. Yet its gravitational pull is so powerful that without it, galaxies would fly apart, and the universe as we know it wouldn't exist. Here's how it works. When the universe was young, dark matter's gravity began pulling tiny clumps of matter together, creating dense regions where galaxies would eventually form. Ordinary matter, the stuff we're made of, was too hot and energetic to settle down easily, but dark matter, unaffected by light or radiation, could quietly gather into vast, web-like structures. These cosmic scaffolds became the gravitational anchors for everything else, drawing in gas and dust until stars ignited and galaxies took shape. Even today, dark matter's influence is everywhere. When astronomers measure how galaxies rotate, they find stars on the outer edges moving just as fast as those near the center, defying the laws of gravity as we know them unless there's an invisible mass holding them in place. But the mystery only deepens from there. Despite making up roughly 27% of the universe's total mass and energy, we still don't know what dark matter actually is. Is it a sea of undiscovered particles, like WIMP weakly interacting massive particles floating through space? Or could it be something even stranger, like primordial black holes formed in the universe's first moments? Experiments deep underground, in abandoned mines and beneath mountains, are hunting for these elusive particles, while telescopes scan the skies for subtle distortions in starlight caused by dark matter's gravity. What's fascinating is how dark matter maintains the universe's delicate balance. Without it, the cosmos would either be too smooth, with matter spread too thinly to form galaxies, or too clumpy, collapsing into black holes before life could emerge. Instead, dark matter's gravitational touch created just enough structure to build galaxies, stars, and planets, while leaving the overall universe remarkably uniform on the largest scales. It's a reminder that the forces shaping the cosmos are often hidden, operating in the shadows, yet without them, none of us would be here to marvel at the stars. And here's the tantalizing part. dark matter isn't just holding galaxies together. It might be the key to understanding why the universe looks the same everywhere. Its gravitational influence helped smooth out early irregularities, reinforcing the uniformity we see in the cosmic microwave background. Yet despite its pivotal role, dark matter remains one of science's greatest unsolved riddles, a ghostly presence woven into the fabric of reality, waiting to be unmasked. Dark energy is the universe's silent enforcer, a mysterious force pushing galaxies apart at ever-increasing speeds. Imagine blowing up a balloon with glitter scattered inside. As the balloon expands, the glitter moves away from every other speck, not because the glitter itself is moving, but because the space between it is stretching. That's what dark energy does to the cosmos, stretching the fabric of space itself so that over time, even the closest galaxies will eventually vanish from view, their light stretched beyond detectability. Yet this relentless expansion isn't just about distance, it's about preserving the universe's grand uniformity. Here's the paradox: gravity should be slowing the universe's expansion, pulling galaxies closer together over time. Instead, observations of distant supernova in the late 1990s revealed the opposite. The expansion is speeding up, as if some invisible hand is pressing harder on the cosmic accelerator. Dark energy, making up roughly 68% of the universe's total energy, is that unseen driver. By counteracting gravity's pull, it prevents matter from clumping too densely on the largest scales, maintaining the smoothness we see in the cosmic microwave background. Without dark energy's repulsive push, the universe might have collapsed into a chaotic patchwork of over-dense regions, breaking the cosmological principle's elegant symmetry. But what is dark energy? The leading explanation points to the vacuum of space itself, not empty, but seething with quantum fluctuations that generate a kind of anti-gravity. Einstein once proposed a similar idea with his cosmological constant, a mathematical fudge factor he later called his greatest blunder. Ironically, modern measurements suggest he might have been right all along. Empty space could possess an innate energy density that drives cosmic acceleration. Yet the numbers don't quite add up. Quantum theory predicts a vacuum energy trillions of times stronger than what we observe, leaving physicists scrambling for alternatives. Could dark energy be a new, undiscovered force? Or is it a sign that Einstein's theory of gravity needs revision on cosmic scales? Some theorists propose even wilder ideas, like phantom energy, a hypothetical form of dark energy that grows stronger over time, potentially tearing apart atoms in a far future Big Rip. Others suggest the acceleration isn't driven by dark energy at all, but by quirks in how we measure cosmic distances. Modified gravity theories, such as MAND, attempt to explain galactic motions without invoking invisible substances, though they struggle to account for the universe's overall uniformity. The truth is, dark energy's dominance marks one of the greatest unsolved puzzles in physics. Its existence reshapes our understanding of cosmic evolution, suggesting that the universe's fate, whether endless expansion, eventual collapse, or something stranger, hinges on a force we can't yet explain. What makes dark energy so fascinating isn't just its mystery, but its timing. For billions of years after the Big Bang, gravity ruled supreme, allowing galaxies and clusters to form. Then, around 5 billion years ago, dark energy took over, as if the cosmos had flipped a switch. Coincidentally, this transition happened around the same time our solar system was forming, a cosmic reminder that the universe's large-scale behavior is intimately tied to the conditions that made life possible. If dark energy had dominated earlier, galaxies might never have formed. If it were weaker, the universe could have collapsed long before stars ignited. Instead, we inhabit a narrow window where both structure and uniformity coexist. a fleeting moment in cosmic history where the questions outnumber the answers, and the night sky's sameness is the deepest clue of all. While inflation theory has become the leading explanation for the universe's remarkable uniformity, it's far from the only game in town. Some cosmologists propose radically different visions of cosmic origins models where the Big Bang wasn't the beginning but merely a turning point in an endless cosmic dance. Take cyclic universe theories, for instance. Picture a cosmos that breathes like a colossal lung, expanding for billions of years before contracting in a big crunch, only to rebound in a new Big Bang. In this mesmerizing scenario, each cycle stretches and smooths the universe like dough being kneaded, wiping away irregularities over countless iterations until matter and energy achieve near-perfect distribution. The appeal of such models lies in their elegant symmetry. Rather than a one-time inflationary event, these theories suggest the universe's sameness emerged gradually through repetitive cycles, each bounce acting like a cosmic reset button that irons out wrinkles from the previous incarnation. Some versions even incorporate string theory's extra dimensions, proposing that our three-dimensional universe collides with a parallel brane in higher dimensional space, triggering new expansion phases. It's a dizzying concept, not just one Big Bang, but an infinite series stretching eternally into past and future. Then there's Roger Penrose's conformal cyclic cosmology, which imagines an even wilder scenario. As the universe expands toward heat death with all matter dissolved into radiation and particles stretched impossibly thin, the distinction between beginning and end blurs. In this distant epoch, the universe becomes so vast and empty that it effectively forgets its scale, allowing the far future to seamlessly connect back to the Big Bang's hot, dense state. The cosmic microwave background's uniform glow might then contain faint imprints of supermassive black holes from a previous eon, like cosmic fingerprints lingering across cycles of creation. Yet for all their imaginative power, these alternatives face significant hurdles. Unlike inflation, which makes precise predictions about the cosmic microwave background's fluctuation patterns, cyclic models struggle to explain why the universe appears so perfectly flat or why the CMB's temperature variations follow such specific statistical distributions. More critically, there's no observational evidence yet for a preceding cosmic cycle or higher dimensional collisions. That's not to say these ideas are wrong, only that inflation currently fits the data better, leaving other theories in the realm of fascinating but unproven possibilities. What's thrilling is how these competing visions push cosmology forward. The very existence of alternatives forces scientists to sharpen inflation's predictions and seek definitive tests. Future gravitational wave detectors might uncover ripples in spacetime from pre-Big Bang events, or quantum gravity breakthroughs could reveal whether a cyclical universe is mathematically consistent. Until then, the mystery of cosmic uniformity remains open, a reminder that our understanding of the universe's origins is still being written, one bold idea at a time. To understand how quantum fluctuations shape the cosmos, we need to venture into the bizarre realm where quantum mechanics meets cosmology. Picture the early universe not as a smooth, placid soup, but as a seething quantum froth, a storm of particles popping in and out of existence, governed by the strange rules that dominate the subatomic world. In this microscopic chaos, tiny fluctuations in energy density flickered unpredictably, lasting mere fractions of a second before vanishing. Normally, these quantum jitters would be too small to matter, lost in the noise of particle interactions. But inflation, the universe's explosive initial growth, changed everything. As space expanded faster than light, those fleeting quantum ripples were stretched to cosmic proportions, frozen into the fabric of spacetime like grooves on a vinyl record. What were once fluctuations smaller than a proton became imprints spanning millions of light years, subtle variations in density that gravity would later amplify into galaxies and voids. It's as if someone took a handful of confetti, each piece representing a quantum wobble, and stretched it into a vast tapestry where each thread became a galaxy cluster. The cosmic microwave background's temperature variations, those millionth of a degree differences, are essentially quantum whispers amplified to cosmic shouts. This connection between the infinitesimally small and the astronomically large is one of the most startling revelations in modern physics. Quantum mechanics, which governs particles trillions of times smaller than atoms, somehow wrote the blueprint for structures billions of light years across. Consider that every galaxy, every star, every planet owes its existence to these random subatomic flickers, a humbling reminder that the universe's grandest structures grew from the tiniest seeds of uncertainty. Yet mysteries remain. Why did inflation preserve these particular fluctuations while smoothing out everything else? Some theories suggest these quantum ripples weren't entirely random, but followed patterns encoded in the physics of the early universe, like waves on a pond freezing mid-ripple. Others propose that what we see as quantum fluctuations might be shadows of even deeper processes, perhaps vibrations of cosmic strings or echoes from dimensions beyond our own. The more we learn, the clearer it becomes. The universe's uniformity isn't just a happy accident. It's a delicate dance between quantum randomness and cosmic order, where the smallest things shape the largest. And here's what's truly mind-bending. If quantum fluctuations had been slightly stronger, matter might have clumped too densely, collapsing into black holes before stars could form. Slightly weaker, and galaxies might never have coalesced at all. We exist because these fluctuations hit a Goldilocks sweet spot, another stroke of cosmic luck, in a universe that seems oddly fine-tuned for complexity. This quantum cosmic bridge doesn't just explain why the night sky looks similar everywhere. It hints that the universe's deepest laws operate seamlessly across all scales, from the quantum foam to the cosmic web. The horizon problem is like walking into two separate rooms on opposite sides of the planet and finding them set to exactly the same temperature down to a fraction of a degree, even though they've never shared a heating system or even a single conversation. That's the enigma cosmologists face when studying the cosmic microwave background. Regions of the universe separated by billions of light years, regions so distant that light hasn't had time to travel between them since the Big Bang, display identical temperatures with eerie precision. According to classical physics, this shouldn't be possible. Heat needs time to distribute evenly, and without any mechanism to synchronize these regions, they should vary wildly in temperature. Yet the universe defies expectation, presenting us with a puzzle that challenges our deepest understanding of space and time. Inflation theory offers an elegant solution. These seemingly disconnected patches of space were once neighbors, packed together in the universe's infancy before being violently wrenched apart by exponential expansion. Imagine two dots painted side by side on a deflated balloon. When you blow it up, they race away from each other, but their shared origin explains why they still match perfectly. Inflation stretched the universe so rapidly that regions now on opposite sides of the sky were once close enough to exchange heat, achieving thermal equilibrium before being separated faster than light could bridge the growing gap. But inflation isn't the only possible explanation. Some theorists propose even wilder ideas, like variable speed of light cosmologies, the notion that light traveled much faster in the early universe, allowing distant regions to communicate and equalize temperatures before settling into today's constant speed. It's a radical departure from Einstein's relativity, but if light speed wasn't always fixed, it could explain the horizon problem without invoking inflation. Others explore models where the fundamental constants of nature, like the strength of gravity or electromagnetism, fluctuated in the universe's first moments, creating temporary conditions that enabled instantaneous thermal mixing. Perhaps the most mind-bending alternative comes from quantum entanglement, the strange phenomenon where particles remain mysteriously linked across vast distances, instantaneously influencing each other's states. Could the entire universe have been quantum entangled at birth, with particles communicating faster than light to synchronize temperatures? It's a tantalizing thought, though scaling quantum weirdness to cosmic proportions presents staggering mathematical challenges. What's fascinating is how each solution reflects a different philosophical approach to cosmology. Inflation reshapes our view of spacetime's expansion, variable light speed tweaks nature's constants, and quantum entanglement leans on the universe's inherent interconnectedness. Yet they all converge on the same truth: the universe's uniformity isn't just a lucky accident. It's a clue written in the oldest light we can see, pointing us toward the mechanisms that forged reality itself. And as we peel back these layers, we're not just solving a puzzle, we're learning how deeply the cosmos is woven together, from its smallest particles to its grandest scales. The idea of a multiverse isn't just science fiction. It's a serious scientific hypothesis that could explain why our universe appears so finely tuned for life. Picture a colossal cosmic foam where each bubble is a separate universe with its own unique laws of physics. Some might have stronger gravity, others might lack electromagnetism entirely, and a rare few, like ours, might strike the perfect balance for stars, planets, and life to emerge. This isn't just wild speculation. It's a natural extension of inflation theory, which suggests that the same exponential expansion that smoothed our universe could be happening endlessly, birthing new universes beyond our cosmic horizon. But how could inflation create multiple universes? Think of it like boiling water. When heated, bubbles form and detach, each representing a pocket where inflation has ended, giving rise to a new universe. In this scenario, our universe is just one bubble in an infinite cosmic sea, each with its own distinct properties. Some might collapse instantly, while others could stretch endlessly without forming stars. We happen to inhabit one where the conditions are just right, a cosmic Goldilocks zone where the uniformity we observe is merely a local phenomenon. The real question is whether we could ever detect evidence of other universes. Some theories suggest that if two bubble universes collided, the impact might leave a faint imprint in the cosmic microwave background, a kind of cosmic bruise on the sky. Astronomers have searched for these anomalies, but so far, no definitive signs have emerged. Other proposals involve looking for subtle gravitational effects at the edges of our observable universe, or even searching for quantum entanglement between universes, though these ideas push the limits of current technology. Critics argue that the multiverse is untestable by definition. If other universes are forever beyond our reach, how can we ever confirm their existence? Yet supporters counter that the idea isn't purely speculative. The same physics that predicts inflation also naturally leads to the multiverse concept. And if we accept that inflation happened once, why wouldn't it happen countless times across an eternally expanding landscape? What's fascinating is how the multiverse could solve one of cosmology's biggest puzzles: the fine-tuning problem. Our universe's constants, the strength of gravity, the mass of electrons, are exquisitely balanced for complexity. If they were even slightly different, life as we know it couldn't exist. The multiverse offers an elegant explanation. In an infinite array of universes, every possible combination of constants exists somewhere. We simply find ourselves in one where the numbers work. Even if we never prove the multiverse is real, the concept reshapes how we think about our place in the cosmos. It suggests that the uniformity we see might not be a fundamental rule but a quirk of our local bubble. And if that's true, the universe isn't just vast. It's one of countless others, each with its own story, its own laws, and perhaps its own version of someone peering up at the stars, wondering if they're alone. String theory weaves an astonishing possibility that the universe's uniformity might be written in dimensions we can't even see. Imagine our cosmos as a vast, three-dimensional shadow cast by vibrations in a higher dimensional space, like ripples on the surface of a pond creating patterns in the depths below. In this framework, the startling consistency of physical laws across billions of light years could arise from these hidden dimensions acting as cosmic tuning pegs, subtly adjusting the fundamental constants that govern reality. At the heart of string theory lies a radical idea. The particles making up our universe aren't tiny dots but unimaginably small, vibrating strings. Their different frequencies produce the variety of particles we observe, from quarks to photons. But here's where it gets cosmic. These strings don't just wiggle in the familiar 3 dimensions. They dance through 10 or 11 dimensions, with all but our everyday 3 curled up into spaces smaller than an atom. The way these extra dimensions fold and twist could determine why gravity is so weak compared to other forces, why the cosmological constant has its precise value, and ultimately, why the universe appears so uniform on large scales. One compelling string theory concept, the landscape of possible universes, suggests there could be 10 to the 500 unique configurations of these extra dimensions, each corresponding to a universe with different physical laws. Our universe's particular configuration might naturally lead to the smooth, homogeneous cosmos we observe. It's as if the higher dimensional geometry acts like a cosmic mold, imprinting uniformity across our 3-dimensional reality. Some versions even propose that colliding higher dimensional branes could have triggered our Big Bang, spreading matter and energy evenly from the outset. Yet for all its mathematical elegance, string theory faces towering obstacles. No experiment has yet detected these extra dimensions or the strings themselves. The energy scales required to probe them are trillions of times beyond what particle colliders like the Large Hadron Collider can achieve. Some critics argue this makes string theory more philosophy than science, a beautiful idea forever beyond empirical reach. But supporters counter that indirect evidence might still emerge, perhaps through subtle imprints in the cosmic microwave background or unexpected patterns in particle interactions. What makes string theory tantalizing isn't just its potential to explain cosmic uniformity, but how it redefines our notion of reality. If correct, the night sky's sameness isn't just a feature of our universe, it's a signature of deeper, hidden dimensions that shape existence itself. Until we find a way to test these ideas, string theory remains a dazzling hypothesis, a reminder that the universe's greatest secrets might be hiding in dimensions we've yet to perceive. The Anthropic Principle turns the question of cosmic uniformity upside down. Instead of asking why the universe is so smooth, it suggests that the answer might lie in the fact that we're here to observe it. Think about it like this: if the universe were too lumpy, with matter clumped unevenly in some regions and nearly empty in others, galaxies might never have formed. Too smooth, and gravity wouldn't have had enough variation to pull matter together into stars and planets. The very fact that we exist to ponder this mystery implies the universe had to strike a delicate balance, a Goldilocks zone of uniformity that allowed complexity and eventually life to emerge. But this idea walks a fine line between profound insight and circular reasoning. On one hand, it's a reminder that the laws of physics and the initial conditions of the cosmos seem eerily fine-tuned for life. The cosmological constant, the strength of gravity, even the slight density variations in the early universe tweak any of these even slightly, and the result would be a sterile void or a chaotic mess. In this sense, the anthropic principle is almost tautological. We observe the universe to be uniform because only a universe with that uniformity could produce observers. Critics argue this explanation feels like a cosmic shrug. It doesn't actually explain why the universe is uniform, only that we shouldn't be surprised it is. It's like finding a perfectly tuned radio in the desert and concluding, well, if it weren't tuned, I wouldn't be here to hear it. That might be true, but it doesn't tell us who built the radio or how it works. Some scientists worry that invoking the anthropic principle could stifle deeper investigation, offering a philosophical stopgap where physics should keep probing. Yet there's a compelling counterpoint, the multiverse. If infinite universes exist with different physical constants, the anthropic principle becomes a statistical inevitability. We simply live in one of the rare universes where conditions allowed life to arise. In this framework, cosmic uniformity isn't a mystery to solve but a selection effect, like winning the lottery and realizing someone had to. The challenge is testing this idea. How do we distinguish a universe designed for life from one that just happens to fit the bill by chance? What makes the anthropic principle so provocative isn't just its implications for cosmology, but how it bridges science and philosophy. It forces us to confront whether the universe's uniformity is a brute fact, a divine blueprint, or just one roll of the dice in an infinite cosmic casino. And while it might not provide definitive answers, it reshapes the questions we ask, reminding us that the night sky's sameness isn't just a feature of the cosmos, but a precondition for our existence. Zoom in on any patch of the night sky, and you'll find chaos galaxies colliding, stars exploding, planets orbiting in dizzying patterns. But pull back far enough, and all that wild diversity melts into a serene sameness, like individual brushstrokes blending into a single hue on a painter's canvas. This cosmic dichotomy, frenetic variation up close, flawless uniformity at a distance, is one of the universe's most elegant tricks, and it all comes down to two competing forces: gravity's relentless pull and dark energy's relentless push. On small scales, gravity reigns supreme. It's the sculptor of cosmic neighborhoods, pulling gas clouds into stars, stars into galaxies, and galaxies into sprawling clusters. Those slight density variations in the early universe, the ones imprinted by quantum fluctuations, became gravity's raw material. Over billions of years, matter pooled in the denser regions, like water gathering in the dips of a wrinkled sheet. The result, a universe teeming with structure where no two galaxies look exactly alike. Yet on the grandest scales, something extraordinary happens. Dark energy, the mysterious force accelerating the universe's expansion, overpowers gravity's grip. Picture a vast ocean where waves of galaxies rise and fall, but the water itself stretches endlessly in all directions, diluting any large-scale unevenness. This is why, when astronomers map millions of galaxies, they don't see a chaotic jumble but a cosmic web so evenly distributed that it resembles foam on a perfectly poured beer. The farther apart galaxies are, the faster dark energy pushes them apart, ensuring no single region dominates the cosmic landscape. The real magic lies in the timing. For the first half of cosmic history, gravity had the upper hand, weaving galaxies into existence. But around 5 billion years ago, dark energy took over, hitting the brakes on large-scale clustering just as the universe reached its ideal balance. Structured enough for life, but smooth enough to obey the cosmological principle. If dark energy had kicked in earlier, galaxies might never have formed. If it arrived later, the universe could have become a patchwork of overcrowded superclusters and barren voids. Instead, we inhabit a universe where both extremes coexist, where the same laws that crafted Earth's mountains also ensure the cosmos, on average, looks the same in every direction. This delicate dance between chaos and order isn't just a cosmic curiosity, it's the reason we're here. A universe without small-scale variation would lack the ingredients for planets and life. One without large-scale uniformity would defy the very laws that make physics predictable. The night sky's secret is this: the universe is a master of balance, playing both sides against the middle to create a stage where complexity can flourish against a backdrop of perfect symmetry. Dark energy's grip on the cosmos is only tightening, and the universe's future may be one of growing loneliness. Picture a vast cosmic party where guests, galaxies, stars, and even the faintest whispers of light are slowly but surely drifting apart. As dark energy accelerates the expansion of space itself, clusters of galaxies that once felt like neighbors will become isolated islands, separated by ever-widening gulfs of emptiness. Over trillions of years, the night sky as we know it will fade. The Milky Way's local group might remain gravitationally bound, but everything beyond will redshift into oblivion, their light stretched so far that even the most powerful telescopes of the far future would see only darkness. This isn't just a poetic metaphor, it's the inevitable conclusion of current cosmological models. The universe's uniformity won't just persist, it will intensify. With galaxies pushed beyond one another's event horizons, the cosmic web will unravel, leaving no trace of the structures we see today. Future astronomers, if any exist, might gaze up at a sky where their own galaxy is the only visible object, with no external reference points to confirm the universe was ever anything but a static, empty void. The cosmic microwave background, that ancient echo of the Big Bang, will have redshifted into undetectability, erasing the last clues of the universe's fiery birth. Yet this raises a profound question for cosmology. How will we study a universe that's actively hiding its own history? Already, astronomers worry about the missing universe problem. The fact that we can only observe a fraction of what's out there due to dark energy's acceleration. In the distant future, that fraction will shrink to zero. Some theorists speculate that civilizations born billions of years from now might never deduce the Big Bang or cosmic expansion, living in a reality where the universe appears eternal and unchanging. It's a sobering thought. The very forces that made the cosmos comprehensible to us may one day render it incomprehensible to others. But there's a twist. Even as dark energy smooths the universe on the largest scales, gravity's local dominance ensures some structure will endure. Supermassive black holes, the last remnants of galactic cores, might orbit one another for epochs longer than the current age of the universe. Their slow dance is the only motion in an otherwise static cosmos. And in the far, far future, quantum tunneling could eventually dissolve even these titans into radiation, leaving behind a universe so uniform that not even atoms remain. What does this mean for the quest to understand cosmic uniformity? It suggests that we're living in a uniquely privileged era, a golden age of cosmology where we can still trace the universe's history from its explosive birth to its accelerating present. The very fact that we see galaxies clustering and background radiation is a fleeting window, one that won't stay open forever. Future civilizations might lack the context to even ask why the universe is the same everywhere, because from their perspective, it always was. Our ability to ponder this mystery, then, is as much a product of timing as it is of intellect. The cosmos gave us just enough time to glimpse its secrets before they slip away into the expanding dark. The James Webb Space Telescope isn't just another instrument, it's a time machine, capable of capturing light from the universe's first galaxies, formed when the cosmos was less than 5% of its current age. Unlike Hubble, which peered into the visible spectrum, Webb's infrared eyes can see through cosmic dust and detect wavelengths stretched by the expansion of space itself. This means we're not just getting sharper images, we're uncovering snapshots of the universe's toddler years, when the first stars ignited and the earliest structures began to form. What astronomers hope to find are clues about how the pristine uniformity of the Big Bang gave rise to the intricate cosmic web we see today. One of Webb's most exciting targets is the epoch of reionization, a pivotal chapter when the first starlight began punching holes in the fog of neutral hydrogen that filled the early universe. By studying these ancient bubbles of ionized gas, scientists can trace how matter started clustering, testing whether inflation's predictions about those initial quantum fluctuations hold up. Already, Webb has spotted galaxies far brighter and more massive than models predicted, raising questions about whether dark matter played a bigger role in early structure formation than we thought. Every unexpected discovery is a potential crack in our understanding, a hint that the universe's smooth beginnings might hide complexities we've yet to imagine. But Webb isn't working alone. The upcoming Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will map the cosmos in wide-field surveys, measuring the distribution of millions of galaxies with unprecedented precision. Where Webb zooms in, Roman zooms out, revealing the large-scale structure of the universe in a way that could pinpoint deviations from uniformity. Together, these telescopes act like cosmic detectives, one examining the fingerprints of the early universe, the other reconstructing the crime scene billions of years later. Ground-based observatories are joining the hunt too. The Vera C. Rubin Observatory's legacy survey of space and time will scan the entire southern sky every few nights, creating a time-lapse movie of the cosmos that could uncover subtle changes in galactic motions or the expansion rate. Meanwhile, next-generation spectrographs like those on the extremely large telescope will analyze the chemical composition of the universe's first stars, searching for anomalies that might rewrite our theories about cosmic evolution. The most tantalizing possibility: these instruments might uncover evidence of primordial gravitational waves, ripples in spacetime from inflation itself. While experiments like BICEP have hunted for their imprint in the cosmic microwave background, future detectors could spot them directly, offering a clear signal from the universe's first trillionth of a second. Finding these waves would be like discovering the fingerprints of the cosmic architect, confirming not just that inflation happened, but how. What makes this era so revolutionary isn't just the technology, but the questions we're finally equipped to ask. Are there fundamental flaws in our models of cosmic uniformity? Could the universe's large-scale structure reveal hidden forces or dimensions? With each new observation, we're not just filling gaps in our knowledge, we're testing the very foundations of cosmology. And the answers, whatever they are, will reshape our understanding of everything from the Big Bang to the fate of the cosmos. The universe's eerie uniformity doesn't just challenge physicists, it sends philosophers spinning. Why should reality, in all its vastness, obey such precise, predictable rules? Why does the same gravitational constant hold true in a distant galaxy as it does here on Earth? For some, this cosmic consistency hints at something deeper, a fundamental order woven into the fabric of existence, a set of laws so elegant that they transcend time and space. Others see it as a cosmic roll of the dice. We just happen to live in the one universe where conditions align perfectly for structure, life, and curiosity to emerge. Think of it like walking into a library where every book, no matter how different its story, follows the same grammatical rules. The universe, in this sense, is a grand narrative written in a language of mathematics and physics, with chapters that unfold from the Big Bang to the formation of galaxies, all adhering to the same syntax. This isn't just convenient for scientists, it's downright mysterious. Why should nature be so comprehensible? Why should human minds, products of evolution on a tiny planet, be capable of deciphering the universe's deepest secrets? Some philosophers argue this isn't a coincidence at all. The rational intelligibility of the cosmos, as Einstein called it, might reflect a profound connection between our minds and the universe itself, a kind of cosmic resonance that allows us to decode its patterns. Others take a more pragmatic view. If the universe weren't uniform and predictable, we wouldn't be here to question it. In a chaotic, lawless cosmos, life might never have gained a foothold, let alone develop the capacity to ponder its origins. Yet the uniformity also raises existential questions. If the cosmos is so vast and so homogeneous, does that make humanity insignificant, a fleeting speck in an endless, repeating pattern? Or does it make our ability to comprehend the universe all the more remarkable? The ancient Greeks saw order in the heavens as evidence of divine craftsmanship, while modern thinkers like Carl Sagan framed it as a call to exploration, a reminder that we're not just observers of the cosmos but participants in its story. Perhaps the most humbling idea is that our entire universe, with all its galaxies and laws, might be just one possibility in an unfathomable multiverse, a single thread in a tapestry of realities, each with its own rules. In that context, uniformity isn't a universal truth but a local accident, a quirk of our particular cosmic neighborhood. Whether you find that thought liberating or unsettling, it's a reminder that the night sky's sameness isn't just a scientific puzzle. It's a mirror reflecting our deepest questions about meaning, purpose, and our place in the grand scheme of things. The universe's grand uniformity is one of cosmology's bedrock principles, but what happens when the cosmos throws us a curveball? Enter the Hercules Corona Borealis Great Wall, a colossal filament of galaxies stretching over 10 billion light-years, so vast it challenges our understanding of cosmic structure. Picture a mountain range where the tallest peak shouldn't, by all accounts, exist, yet there it stands, defying the smooth cosmic landscape we expect. This isn't just a statistical fluke, it's a potential crack in the foundation of the cosmological principle, the idea that the universe should look roughly the same in every direction on large scales. How could such a structure form? According to standard models, the universe's expansion and the limited speed of light impose a theoretical maximum size for cosmic features about 1.2 billion light-years. Anything larger shouldn't have had enough time to coalesce under gravity's pull. Yet the Hercules Corona Borealis Great Wall dwarfs that limit, spanning nearly 10 times the expected scale. It's as if archaeologists dug up a single brick and found it was the size of a continent. Some scientists argue this could be a rare statistical outlier, a cosmic jackpot where random density fluctuations lined up by chance. Others wonder if it's evidence of exotic physics, perhaps primordial energy fields left over from inflation that warped spacetime on unimaginable scales. But this isn't the only anomaly. The cold spot in the cosmic microwave background, a frigid region spanning hundreds of millions of light-years, has long puzzled astronomers. Could it be a shadow cast by a supervoid, a near-empty region of space where matter is unusually sparse? Or something stranger, like a collision between our universe and another bubble in the multiverse? Then there's the mysterious axis of evil, an alignment of temperature fluctuations in the CMB that seems to point in a preferred direction, as if the universe has a subtle north and south. These aren't just quirks, they're potential clues that the cosmos might not be as uniform as we thought. The stakes couldn't be higher. If these structures are real, not just artifacts of measurement or statistical noise, they could force us to rewrite cosmology's playbook. Maybe inflation didn't smooth the universe as perfectly as we believed, leaving behind wrinkles we're only now detecting. Or perhaps dark energy behaves differently on colossal scales, sculpting matter into mega structures we don't yet understand. There's even a fringe theory that these anomalies are signatures of a higher dimensional universe imprinting itself on our three-dimensional reality, like a hand pressing against a sheet of fabric. Yet skepticism remains. The farther we look into space, the trickier measurements become. Galactic surveys might miss faint structures, or apparent anomalies could vanish with better data. The Planck satellite's detailed maps of the CMB, for instance, showed the cold spot is slightly less extreme than earlier observations suggested. And some simulations indicate that gargantuan structures like the Hercules Corona Borealis Great Wall might not be impossible, just extraordinarily unlikely, like rolling 1,000 dice and getting all sixes. What's thrilling is how these cosmic oddities push science forward. Every anomaly is a question, and every question refines our models. Future telescopes, like the European Space Agency's Euclid mission, will map the universe in 3 dimensions, testing whether these structures are truly breaks in uniformity or just the universe's way of keeping us humble. After all, if cosmology has taught us anything, it's that the cosmos loves a good surprise, and the biggest revelations often start with the simplest question. Wait, that shouldn't be there, should it? Cosmic inflation might be the leading explanation for the universe's uniformity, but not everyone in the scientific community is convinced. Some physicists argue that inflation has become a theory of everything and nothing, so adaptable it can explain almost any observation without ever being definitively proven wrong. Imagine a locksmith who claims their master key can open any door, but when a door resists, they simply tweak the key's shape. Critics say inflation risks becoming that kind of unfalsifiable idea, adjusting its parameters to match whatever new data emerges without offering clear ways to test its core assumptions. One of the most vocal skeptics is Paul Steinhardt, a Princeton physicist who helped pioneer inflation theory in the 1980s but has since become its sharpest critic. He compares inflation to a theory trap, a concept so appealing that it stifles alternative ideas, even when evidence emerges that doesn't quite fit. For instance, while inflation predicts a nearly flat universe, it doesn't strictly require one. If measurements had shown significant curvature, proponents could have adjusted the model to accommodate that too. To Steinhardt, this flexibility isn't a strength but a weakness, blurring the line between science and storytelling. So what are the alternatives? One compelling contender is the bouncing cosmology model, which suggests the Big Bang wasn't the beginning but a rebound from a previous universe's collapse. In this scenario, the universe's uniformity isn't forged in a split-second inflationary burst, but smoothed over countless cycles of expansion and contraction, like dough kneaded repeatedly until perfectly even. Another approach, called emergent gravity, proposes that gravity behaves differently on cosmic scales, eliminating the need for dark matter and offering new ways to explain large-scale structure without relying on inflation's rapid expansion. Then there's the variable speed of light hypothesis, which dares to tweak one of physics' most sacred constants. If light traveled much faster in the early universe, distant regions could have communicated and equalized their temperatures long before inflation would have been necessary. It's a radical idea, one that even its supporters admit would require rewriting textbooks, but it highlights the creativity bubbling at cosmology's frontiers. The debate isn't just academic, it cuts to the heart of how science progresses. inflation's defenders point to its stunning predictive successes, like the precise patterns of temperature variations in the cosmic microwave background. Detractors counter that a good theory should also rule things out, and inflation's ability to predict almost any outcome makes it less a scientific law and more a cosmic Rorschach test. The truth might lie somewhere in between. Future experiments like measurements of primordial gravitational waves or ultra-precise galaxy surveys could tilt the scales, either cementing inflation's dominance or forcing physicists back to the drawing board. What's fascinating is how this tension drives discovery. Every critique of inflation pushes scientists to refine their models, and every alternative theory, no matter how unconventional, expands the universe of possible explanations. Whether inflation stands the test of time or eventually gives way to a new paradigm, one thing is certain: the quest to understand cosmic uniformity is far from over. And that's exactly how science should work, not with dogmatic certainty, but with relentless curiosity, testing every idea until the cosmos reveals its truest face. What if the universe's eerie uniformity isn't a cosmic accident, but a clue that we're living inside an advanced simulation? This isn't just sci-fi speculation. It's a serious hypothesis gaining traction among some physicists and philosophers. The reasoning goes like this: if an intelligent civilization could create hyper-realistic virtual worlds, they'd likely optimize their code for efficiency. A perfectly uniform universe with consistent physical laws and repeating patterns would be far simpler to simulate than a chaotic, unpredictable one. Think of it like a video game designer reusing textures or physics engines to save processing power. The sameness we observe might be a telltale sign of cosmic resource management. Supporters of the simulation argument point to oddities in quantum mechanics as potential glitches in the system. Take the observer effect, where particles seem to choose a state only when measured. Could this be the simulation's way of rendering reality on demand, like a video game loading graphics only when a player looks at them? Even the mathematical elegance of the universe's laws fits the narrative. After all, code runs on math. If reality were a simulation, its creator might rely on clean, algorithmic rules to keep things running smoothly. But critics fire back with a simple question: where's the evidence? Unlike inflation or dark matter, the simulation hypothesis doesn't make testable predictions. It's a philosophical funhouse mirror, interesting to look at, but impossible to grasp. Others argue that uniformity isn't proof of design. It's just what we'd expect from a universe born in a hot, dense Big Bang. And if we're simulations, who's to say our simulators aren't simulations too, leading to an infinite regress of virtual worlds? The debate took a provocative turn when billionaire Elon Musk famously claimed the odds we're in base reality are 1 in billions. His logic: if civilizations ever gain the power to run ancestor simulations, they'd likely create countless iterations, making simulated minds vastly outnumber biological ones. Statistically, we're probably among the digital ones, but philosophers like Nick Bostrom, who formalized the simulation argument, caution that it's not a certainty, just a fascinating possibility worth considering. Here's where things get really mind-bending. If we ever discovered irrefutable proof we're in a simulation, say, a pixelated edge to the universe or a hard-coded limit to computational precision, how would that change our understanding of existence? Would the laws of physics become mere user settings? Could we hack the system? While these questions sound like plot points from the Matrix, they reveal something profound about why the simulation hypothesis captivates us. It's not just about technology, it's about the nature of reality itself, and whether the universe's uniformity is a feature or a flaw in the cosmic code. Ultimately, the simulation hypothesis remains more thought experiment than testable theory, but its persistence in scientific circles speaks to a deeper truth. The universe's sameness is so striking that we'll entertain even the wildest explanations to make sense of it. Whether we're living in a simulation or not, the fact that we can ponder the question at all is its own kind of miracle, one that no amount of code could ever fully replicate. Long before telescopes or quantum physics, humanity gazed at the stars and saw not randomness, but patterned stories woven into the fabric of the night sky. The ancient Egyptians envisioned the heavens as a goddess, Nut, whose arched body stretched uniformly above the earth, her belly dotted with stars that traveled the same path each night. To them, the sky's predictability wasn't a scientific puzzle but a divine promise, a celestial order maintained by gods who kept chaos at bay. Halfway across the world, the indigenous Australians mapped the cosmos through songlines, an intricate web of stories linking stars to landscapes, where the Milky Way's consistent glow served as both navigation tool and cultural touchstone, its uniformity a living library of ancestral knowledge. These myths reveal a universal truth. Every culture that pondered the cosmos recognized its underlying sameness, interpreting it through the lens of their worldview. Hindu cosmology describes a cyclical universe where Brahma's exhale sends galaxies spinning into existence, only for them to dissolve back into the cosmic ocean with his inhale, a rhythm so precise that each cycle mirrors the last. The Norse imagined Yggdrasil, an immense ash tree whose branches held the 9 realms in perfect balance, its roots tethering chaos to order. Even the Babylonian Enuma Elish, one of humanity's oldest creation myths, tells of a primordial unity shattered by gods to form an orderly cosmos, echoing science's own narrative of symmetry broken by inflation. What's striking isn't just the diversity of these stories, but their shared insistence that cosmic uniformity reflects deeper truths. In Chinese philosophy, the Taoist concept of the Tao, the fundamental force flowing through all things, explains nature's consistency as harmony between yin and yang, a dynamic equilibrium sustaining the heavens. The Maya tracked Venus's movements with such precision that their astronomical tables predicted its cycle centuries in advance, seeing in its regularity a sacred calendar governing both celestial and human affairs. These traditions didn't merely observe the universe's order, they revered it as sacred, a reflection of moral or spiritual laws as binding as gravity. Fast forward to the scientific revolution, and the quest for cosmic understanding took a new turn. Galileo's telescope revealed moons orbiting Jupiter, proving Earth wasn't the center of all motion. Yet even in this upheaval, the universe's underlying uniformity became a guiding principle. Newton's laws showed that apples and planets obeyed the same gravity, while Einstein's relativity revealed spacetime as a seamless fabric, warping identically whether near a star or a galaxy. Science, in its own way, became a kind of mythos not of gods, but of equations where the universe's sameness pointed not to divine will, but to universal constants. Yet the most poignant connection between ancient and modern lies in what these perspectives share, a humbling acknowledgement that the cosmos operates by rules far beyond human whim. Whether through ritual or radar, prayer or particle accelerators, we've always sought to decipher why the universe plays by the same rules everywhere. That pursuit, part science, part spirituality, reminds us that our drive to understand cosmic uniformity isn't just about physics. It's about finding our place in a grand, ordered whole, where the stars that guided Polynesian navigators millennia ago still shine with the same light our telescopes study today. The languages change, but the question endures. In a cosmos so vast, why does it all feel so familiar? sharing the mysteries of cosmic uniformity isn't just for scientists, it's a gateway to igniting wonder in minds of all ages. Picture a child gazing up at a planetarium dome, where a projection of the cosmic microwave background unfolds like a celestial quilt, each tiny fluctuation a stitch in the fabric of the universe. Or a teenager watching a documentary that compares inflation to blowing up a balloon, transforming abstract physics into something tactile and vivid. These moments of connection don't just educate, they spark a lifelong curiosity about our place in the cosmos. The best science communicators understand that explaining the universe's sameness isn't about dumping facts, it's about crafting stories that resonate, using metaphors that stick, and finding creative ways to make the unimaginable feel personal. Take the work of astrophysicist Neil deGrasse Tyson, whose knack for blending humor with cosmic scale turns complex ideas into relatable anecdotes. When he describes the universe's uniformity as the ultimate group project, where every galaxy followed the same instructions, suddenly, the cosmological principle feels less like a textbook term and more like a shared human experience. Or consider YouTube creators like Veritasium and PBS Spacetime, who use animations and thought experiments to visualize how dark energy stretches space or how quantum fluctuations seeded galaxies. By meeting viewers where they are, whether through bite-sized videos or deep-dive podcasts, these communicators bridge the gap between cutting-edge research and everyday curiosity. But the challenge goes beyond making content engaging. It's about dismantling barriers to access. Many planetariums now offer shows in multiple languages, while podcasts like Star Talk translate cosmic concepts into plain-spoken dialogue. Interactive exhibits at science museums let visitors play with models of the early universe, adjusting inflation parameters to see how slight changes could lead to a chaotic cosmos or a sterile void. Even social media has become a frontier for democratizing knowledge, with astronomers like Katie Mack using Twitter threads to debunk myths about the Big Bang, or TikTok creators using visual effects to simulate the stretching of spacetime. The most effective strategies share a common thread. They treat the audience as collaborators, not passive recipients. When the European Space Agency released raw data from the Planck satellite, citizen scientists helped analyze it, uncovering patterns that professional researchers might have missed. Crowdsourced projects like Galaxy Zoo invite anyone with an internet connection to classify distant galaxies, turning the hunt for cosmic structure into a global team effort. This participatory approach doesn't just educate, it empowers, fostering a sense of ownership over humanity's collective quest to understand the universe. Yet there's still room to grow. Too often, science communication defaults to a one-size-fits-all model, overlooking audiences who might engage differently with the material. For some, the precision of a technical lecture is thrilling. For others, a poetic narrative about the night sky's sameness might be the key that unlocks fascination. The next frontier could lie in virtual reality, where users step inside simulations of the early universe, watching inflation unfold around them in real time. Or in partnerships with artists, like the composer who translated CMB temperature fluctuations into a symphony, letting listeners hear the birth of the cosmos. The goal isn't just to inform, it's to inspire a deeper relationship with the cosmos, one where the universe's grand uniformity isn't a distant abstraction, but a shared story we're all part of. When a sixth grader realizes that the same quantum rules governing their phone's silicon chips also shaped galaxy clusters, or when a retiree attending a public lecture grasps how dark energy's push counteracts gravity's pull, those aren't just lightbulb moments. They're reminders that the universe's mysteries belong to everyone, and that the urge to look up and ask why connects us across cultures, generations, and even time itself. For all we've uncovered about the universe's uniformity, the deepest mysteries still loom, large puzzles so profound they redefine what we think we know. Take inflation, that split-second exponential expansion that ironed out the cosmos. We can model its effects with stunning precision, tracing how quantum fluctuations became galactic seeds. Yet the trigger, the cosmic spark that set it off, remains utterly unknown. Was it a phase transition, like steam condensing into water, releasing latent energy that propelled space outward? Or something more exotic, a collision between higher dimensional brains in string theory's tangled landscape? The harder we look, the stranger the possibilities become. Then there's dark energy, the phantom force accelerating the universe's expansion. We measure its influence in the redshift of distant supernova, feel its presence in the way galaxy clusters drift apart. But what is it? Einstein's cosmological constant, an energy intrinsic to empty space, fits the data neatly, until you realize quantum field theory predicts a vacuum energy trillions of times stronger than observed. This isn't just a rounding error, it's the worst mismatch in physics history. Some theorists propose dark energy isn't constant at all, but a dynamic field slowly evolving over cosmic time. Others wonder if we're seeing the first cracks in Einstein's relativity, a sign gravity works differently on intergalactic scales. The enigmas multiply when we examine anomalies like the axis of evil, an unexpected alignment in the cosmic microwave background that hints at a preferred direction in space, challenging the cosmological principle's core assumption. Or the baffling Hubble tension, where measurements of the universe's expansion rate disagree depending on whether we use near-by supernova or ancient CMB data. These aren't mere technical glitches. They could be clues pointing to new physics, perhaps extra dimensions, modified gravity, or even a second inflationary epoch we've yet to uncover. What's thrilling is how these unknowns drive innovation. Next-generation telescopes like the Vera-C, Rubin Observatory will map billions of galaxies, hunting for subtle distortions that might reveal dark energy's true nature. Underground labs are chasing hypothetical particles like actions, which could explain both dark matter and aspects of inflation. And gravitational wave detectors, growing ever more sensitive, may soon catch echoes from the universe's first moments, ripples that could confirm or shatter our theories. These aren't abstract quests. Solving them would rewrite our cosmic origin story, answering why the universe looks the way it does, and whether its uniformity is a fleeting phase or an eternal truth. Every unexplained anomaly is a beacon guiding us toward deeper understanding, and that's the essence of science, not just the answers we've found, but the questions that keep us searching. Solving the riddle of cosmic uniformity isn't just a job for astrophysicists, it's a grand collaboration that stretches across disciplines, each bringing a unique lens to the mystery. Take particle physicists, for example. While cosmologists study the vast expanse of the universe, particle researchers focus on the unimaginably small, recreating conditions from the Big Bang in underground colliders like CERN. By smashing particles together at nearly the speed of light, they glimpse the quantum chaos that may have seeded the universe's large-scale smoothness. It's like detectives working a case from opposite ends, one team analyzing fingerprints at the crime scene, the other reverse engineering the suspect's alibi. Together, they're piecing together how quantum fluctuations in the early universe were stretched to cosmic proportions during inflation. But the collaboration doesn't stop there. Mathematicians play a pivotal role, crafting intricate models that simulate the universe's evolution over billions of years. These aren't just abstract equations. Supercomputer simulations like Illustris-TNG use billions of virtual particles to mimic galaxy formation, testing whether theoretical predictions match the real cosmos. When discrepancies arise, like the unexpected brightness of early galaxies spotted by the James Webb Space Telescope, mathematicians tweak their algorithms while astronomers refine their observations, creating a feedback loop that sharpens our understanding. Philosophers, too, weigh in on the conversation, probing the assumptions underlying our theories. When cosmologists invoke the multiverse to explain fine-tuning, philosophers ask, is this science or metaphysics? Can a theory be valid if its alternate universes are inherently unobservable? These debates aren't just academic, they force scientists to articulate clearer standards for evidence, pushing cosmology toward more rigorous foundations. The most exciting breakthroughs often happen at these disciplinary crossroads. Consider how gravitational wave astronomy, born from Einstein's math, enabled by engineering feats like LIGO, now offers a new way to test inflation. If primordial gravitational waves are ever detected, they could reveal energy levels from the universe's first moments, bridging quantum mechanics and general relativity. Similarly, dark matter research blends astrophysical observations with particle physics experiments, as teams hunt for WIMP in abandoned mines and neutrino detectors. This interdisciplinary synergy is reshaping how we approach cosmic questions. When the Event Horizon Telescope captured the first image of a black hole's shadow, it required not just astronomers but computer scientists, statisticians, and even meteorologists to synchronize telescopes across the globe and process petabytes of data. The resulting image didn't just confirm Einstein's predictions, it showcased how diverse expertise can illuminate the universe's deepest secrets. The takeaway: cosmic uniformity isn't a puzzle to be solved in isolation. It's a mosaic where each discipline contributes a piece, whether it's a physicist modeling quark-gluon plasma, a philosopher questioning the nature of scientific truth, or a data engineer designing algorithms to filter cosmic noise. And as these threads weave together, they're not just answering old questions, they're uncovering new ones, proving that the universe's greatest mysteries are best tackled by minds working in concert. Imagine making a cosmic discovery from your backyard, no PhD required. That's the power of citizen science, where everyday stargazers and data enthusiasts are revolutionizing cosmology alongside professionals. Projects like Galaxy Zoo have turned millions of volunteers into cosmic cartographers, classifying distant galaxies from telescope images with accuracy rivaling supercomputers. One participant even spotted a never-before-seen celestial oddity now nicknamed Hanny's Vorwerp, a glowing green blob that turned out to be a quasar's ghostly echo. It's proof that cosmic breakthroughs aren't just for observatories, they can start with a curious person clicking through galaxies on a laptop. The tools to participate have never been more accessible. Platforms like Zooniverse host dozens of astronomy projects, from hunting for exoplanets in NASA data to tracking asteroid rotations. Amateur astronomers with modest telescopes can join the American Association of Variable Star Observers, contributing measurements that help professionals study pulsating stars or supernova. Even smartphone apps like Globe at Night let you log light pollution levels, aiding research on how artificial brightness obscures our view of the cosmos. The data you submit might calibrate satellite instruments or refine models of galactic evolution, small actions with interstellar impact. For those who prefer crunching numbers to stargazing, open access datasets are gold mines. The Sloan Digital Sky Survey releases its entire celestial catalog online, allowing anyone to mine it for patterns. High school students have used this data to identify overlooked quasars, while coding enthusiasts train AI to spot gravitational lenses hidden in telescope images. The European Space Agency's Gaia mission shares precise positions of over 1 billion stars, empowering volunteers to map the Milky Way's spiral arms or track runaway stars fleeing their birth clusters. It's like having Hubble's archive on your hard drive, waiting for fresh eyes to spot what algorithms missed. The most thrilling part, these projects aren't just busy work, they address real gaps in research. When professionals face data avalanches like the Vera Rubin Observatory's upcoming flood of 20 terabytes per night, human pattern recognition becomes priceless. Volunteers on the Planet Hunters project helped confirm K2-138, a star system with 5 tightly packed exoplanets, by flagging subtle dips in brightness that machines dismissed as noise. Others sifting through radio signals on SETI at home contributed to the elimination of interference patterns that once masqueraded as alien broadcasts. Every click or classification feeds into papers bearing participants' names, proving science is a team sport where the bench extends globally. Beyond screens, community initiatives like the Asteroid Terrestrial Impact Last Alert System Atlas train amateurs to spot near-Earth objects, turning backyards into early warning networks. Meteor tracking apps transform smartphone cameras into meteoroid detectors, triangulating fireball trajectories across continents. Even vintage astronomy isn't obsolete. Archives like Harvard's 19th century glass plate collection are being digitized by volunteers, revealing century-old stellar explosions that modern telescopes can now revisit. The message is clear. Whether you're sketching Jupiter's storms through an eyepiece or parsing petabytes in Python, there's a universe of discovery waiting for your unique perspective. This democratization of cosmology reflects a profound shift. The universe's secrets aren't locked in ivory towers but scattered like stardust, ready for anyone willing to reach. When a retiree in Portugal spots a supernova or a teen in Mumbai codes a new way to visualize dark matter distributions, they're not just assisting science, they're redefining who gets to call themselves a cosmic explorer. The night sky's uniformity may be a scientific given, but our understanding of it, that's a story still being written by professionals, yes, but also by countless hands and minds gazing upward, asking, what if? Exploring the universe's deepest mysteries isn't just a scientific challenge, it's an ethical one. Every time we point a telescope toward the cosmos or allocate billions to a space mission, we're making a choice. Should we prioritize searching for habitable exoplanets over studying dark energy? Is it ethical to fund a probe to Pluto when Earth faces climate crises? These aren't hypotheticals, they're real dilemmas that scientists, policymakers, and society grapple with. The quest to understand cosmic uniformity isn't happening in a vacuum. It's part of a larger conversation about how we distribute finite resources in pursuit of infinite questions. Take the debate over the James Webb Space Telescope. Its staggering $10 billion price tag sparked fierce discussions. Could that money have been better spent on medicine, education, or renewable energy? Supporters argued that Webb's discoveries, like identifying the chemistry of distant atmospheres, could redefine our place in the universe, while critics saw it as a luxury in a world brimming with urgent needs. This tension isn't new. When Galileo turned his telescope toward Jupiter's moons, he wasn't just making observations, he was challenging the ethical boundaries of knowledge itself, risking heresy charges to expand human understanding. Then there's the question of unintended consequences. Radio telescopes like Arecibo once beamed messages into space, announcing humanity's presence to potential alien civilizations. But what if those signals reached the wrong ears? Renowned scientists like Stephen Hawking warned against reckless communication, comparing it to shouting into a jungle without knowing what predators might answer. While the odds of contact are slim, the stakes, potentially exposing Earth to advanced but hostile civilizations, force us to weigh curiosity against caution. Even the study of cosmic uniformity carries ethical weight. If we someday confirm the multiverse, rendering our universe one of countless others, how might that reshape human identity or purpose? Could it erode our sense of uniqueness or inspire greater humility? History offers cautionary tales. When Copernicus displaced Earth from the universe's center, it triggered not just scientific upheaval but existential crises. Today's discoveries could have similarly profound cultural ripple effects, from religious beliefs to environmental ethics. The way forward isn't about abandoning exploration but embracing mindful stewardship. Initiatives like the IAU's Dark Skies Protection Program show how scientific progress and ethical responsibility can align, combating light pollution to preserve both astronomy and ecosystems. Similarly, NASA planetary protection protocols ensure we don't contaminate other worlds with Earth microbes, or vice versa, blending curiosity with care. Perhaps the ultimate lesson is this: as we unravel why the universe looks the same everywhere, we must also ask who benefits from that knowledge and at what cost. The stars don't give us answers, they mirror back the questions we're brave enough to ask. The quest to unravel the universe's deepest symmetries isn't just about solving equations. It's about passing the torch to those who will write the next chapters of cosmic discovery. Across the globe, a quiet revolution is unfolding as teenagers peer through amateur telescopes, middle schoolers code simulations of inflationary cosmology, and undergraduate researchers analyze galaxy clustering patterns that even seasoned astronomers might overlook. These young minds aren't just learning science, they're reshaping it, armed with fresh perspectives that often challenge conventional wisdom. Consider the story of Nicole Onapuman, who went from building model rockets in a California high school to becoming a first indigenous woman in space, her trajectory proving that cosmic curiosity, when nurtured, can literally reach the stars. Organizations like the Society for Science are democratizing access through competitions like the Regeneron Science Talent Search, where high schoolers present original research on topics ranging from dark matter distributions to quantum fluctuations. One recent finalist developed an algorithm to identify gravitational lensing candidates in telescope data, potentially uncovering new windows into dark matter's invisible web. Meanwhile, initiatives like the African School of Fundamental Physics bring world-class training to students in underrepresented regions, proving that the next Einstein might currently be studying by solar-powered lamp in a rural village. The most effective mentorship often bridges generations. When veteran cosmologist Jocelyn Bell Burnell, discoverer of pulsars, mentors young researchers through the Institute of Physics, she's not just teaching techniques, she's sharing how to persevere when the universe doesn't cooperate. Similarly, online platforms like Zooniverse's Galaxy Zoo let classrooms participate in cutting-edge research, with some student contributions earning co-authorship on peer-reviewed papers. These experiences transform abstract concepts into tangible discoveries, showing kids that scientific breakthroughs aren't just for textbooks, they're happening now and their voices matter. Financial barriers remain formidable, but innovative solutions are emerging. The Breakthrough Junior Challenge awards scholarships for students to create explainer videos about complex physics concepts, while the Thiel Fellowship provides $100,000 to young innovators willing to skip college and dive straight into research. Even smaller-scale efforts, like local astronomy clubs donating refurbished telescopes to Title I schools, can spark lifelong passions. The key is meeting students where they are, whether through TikTok astrophysics explainers, Minecraft recreations of cosmic inflation, or augmented reality apps that let users walk through the large-scale structure of the universe. What makes these efforts so vital isn't just the knowledge they impart, but the questions they inspire. When a ninth grader from Mumbai notices an anomaly in public Kepler Space Telescope data, or when a Navajo high schooler combines traditional star knowledge with Western astronomy to study celestial navigation, they're not just learning, they're expanding how humanity understands the cosmos. The universe's uniformity may be written in the laws of physics, but its story is written by those daring enough to look up and ask why. And as these young explorers will soon discover, the most exciting answers are still waiting in the dark. From the searing intensity of the Big Bang to the relentless push of dark energy, we've journeyed through the incredible forces that shaped our universe into the vast, uniform expanse we see today. It's a story written in quantum fluctuations, stretched across space by inflation, and fine-tuned by the invisible hands of dark matter and dark energy. Yet for every answer we uncover, new mysteries emerge, like the strange alignment of temperature fluctuations in the cosmic microwave background, or the puzzling vastness of structures like the Hercules Corona Borealis Great Wall. These aren't roadblocks, they're invitations to dig deeper, reminders that the cosmos still holds countless secrets waiting to be revealed. What's truly remarkable is how far we've come. Just a century ago, astronomers debated whether the Milky Way was the entire universe. Today, we map galaxies billions of light years away and study the afterglow of creation itself. The James Webb Space Telescope peers back at infant galaxies, while underground labs hunt for elusive dark matter particles. Each breakthrough, whether it confirms our theories or shatters them, adds another piece to the puzzle. And the most exciting part, this isn't just a story for scientists, it's a human story. Every time someone gazes at the night sky and wonders why it looks the same no matter where they stand, they're joining a quest that stretches back to the earliest stargazers and forward to discoveries we can't yet imagine. The universe's uniformity is more than a scientific curiosity. It's a testament to the elegant, interconnected laws that govern everything from the smallest particles to the largest galaxy clusters. It's why physics works the same in a lab on Earth as it does near a black hole, and why we can unravel cosmic history by studying ancient light. But it's also a humbling reminder of how much we don't know. Could there be other universes with entirely different rules? Are we seeing the full picture, or just a shadow of deeper dimensions? These questions push science forward, driving innovations that might one day rewrite our understanding of reality itself. As we close this cosmic journey, remember that the night sky isn't just a spectacle, it's a conversation. Every star, every galaxy, even the empty stretches of space are telling a story about where we came from and how the universe works. You don't need a telescope to be part of it. Sometimes just stepping outside and looking up is enough to spark that sense of wonder. So what do you think? Does the universe's sameness surprise you, or does it feel inevitable? Drop your thoughts in the comments. I love hearing your perspectives. And if you enjoyed this dive into the cosmos, make sure to subscribe and hit that notification bell. There's always more to explore, and I can't wait to share the next cosmic adventure with you. Until then, keep wondering, keep questioning, and never stop looking up. The universe has so much left to show us.